Okay, so some logistics first. Your final exam is Monday, the week after next. I think you all got the time and the location. It's in Phillips Hall. I think 219. I'll send out another email with a reminder. And so just like last year, we'll do a 2-hour exam, or year before that, 2-hour exam. I think we have been allotted 2.5 hours, but it will be a 2-hour exam. And at least in spirit, the exam questions would be similar in section-wise. There'll be some yes, no, or a qualitative, conceptual questions in the beginning, and then at least 2 or maybe 3 problems where you actually calculate things and evaluate. So bring your calculators, open book, same deal as first as both the prelims, open book, open notes, and as far as the contents go, you can. Fair to say, I mean, it's a final, so it will have everything except there'll be a bit more emphasis on the topics that were covered, after the prelim 2, and that's to say, semiconductor diode lasers will be will definitely show up, and the things such as some more details of a standard laser, which were chapter 9, and then others which we discussed will show up as well, right? And you can have a look at the questions from 2 years ago. They give you a feel for what were stressed at that time, and you'd notice that not much semiconductor lasers was done. This year, Professor Pollock and I decided we'll have a bit more discussion of semiconductor lasers, so we did just that. So. Okay, so, and we haven't set up the questions, so we don't know exactly what's in there, but I think you can project from what you have done in your assignments and the problems that you have dealt with. Hopefully the lab will help. It gives you a little more feel of what numbers and things are, what is important in the end when you measure things and such. So any questions on this before we move to other things? And if you do have further questions, please get in touch with me, and I'll try to address them too. Now, the second thing is office hours. It turns out, so essentially I have to do both weekends. So Saturdays, 2 Saturdays, other ones I can actually meet now, and so that's tomorrow afternoon and the next Saturday afternoon. Those are the 2 days I can actually meet, and I'll be in my office. I'll drop and send you an email out that here are the times. And Professor Pollock is around pretty much all of next week. Some of you are hopefully gone and talked to him about your lab too, and you will have some more time of him in the lab when you're doing the setup for the lab, building the laser yourself. So and he has also offered his time for if you want to discuss some concepts and such things. So okay, so yeah.
Will Professor Pollock have a talk?
So what he suggested is he's going to be around during all the lab times, so you can go and bother him and ask him. Yeah.
Are you going to upload the lecture recording?
Yes, they are going to be uploaded as soon as they're finished done editing. So hopefully by this weekend, or if not early next week, they should be available, I think so. And I did, I think Tricia had requested, so I did upload a updated set of slides, but just, I've warned constantly against trying to put too much emphasis on the slides, because they're either from the book or something, it's kind of a rough guidance. But please read the book, and you have solved a lot of problems from the chapter end assignment, so please make sure that you go back, revisit them. Every time you go back, it really increases your understanding, especially with more a bigger picture, you go back and look at the details, it makes much more sense where it fits into this whole picture, argument. So, okay, so I do not intend to discuss too much about the last year's exam or the previous exam, but just put it up here as an example of how it might show up in the end. So, okay, so before I start a short review of the course, what I want to do is kind of emphasize some of the basic principles and end today's class, which is the last class of the semester for us, for this course, by also pointing out where are things going, maybe where we did spend a lot of time trying to understand the science behind the laser, and spent a little bit of time towards the end looking at some of its applications, communications, and a lot of industrial applications for high power lasers and all that. We haven't looked at it in detail, but I think one can project as to where. So those are understood. Those are what one might consider applications that are making use of things that we completely understand about the laser now. Right? So and that's what has led to those applications. But there are quite a few things which we do not completely understand today, and success in understanding them will really lead to future applications which may be much more revolutionary and change things by orders of magnitude than what we imagine is possible today. So I will, obviously it's impossible to say what we don't, what it will lead to. It's, I think, was that Yogi Berra's statement that it's very difficult to predict, especially about the future, right? So, and but if any of you had attended the Hans Bethe lectures this week by Anton Zeilinger as an example, what they're trying to do is communications using photons from lasers, but in a way that no one can eavesdrop. It's completely secure. It's these are entangled photons where basically you split a photon effectively in some sense and then if somebody tries to eavesdrop and detect a signal, an optical signal going through a fiber, for example, it will be known that it was messed with. So that this data was compromised, for example. And so that really is a very interesting interplay of classical understanding of the laser, but more importantly, the fact that you can build a completely coherent or entangled quantum system using photons today. That is, people are just starting to realize that it is possible now, and they're starting to say that obviously lasers have increased the bandwidth for communication, very high data rates and all that, but that adding security to that layer has become one of the biggest challenges today, right? So making secure communication possible, and so. And I think, and many people do think that entangled photons have a very good chance of doing that. So, these are just, we are at a very beginning of that idea. It's not yet clear whether it is going to lead there. Okay, so but then when we started out the course, we had some goals, and hopefully, so the contents, and I'm going to just go through some revision of the topic specifically, but diffraction limited optics, Gaussian beams. If you remember, the first month we spent time looking at how do you combine a monochromatic TEM single mode laser and combine the various modes to make a Gaussian beam. A Gaussian beam in space which decays in real space is not a plane wave. It's completely opposite from a plane wave, not opposite, but very different from a plane wave. A plane wave, if I were to look at an XY plane, has an equal intensity everywhere, right? Perpendicular to its direction of propagation, whereas a Gaussian beam has the intensity goes something like a Gaussian, right? By some length squared, right? So you have to combine many plane waves, take quite a few frequencies and wavelengths, and essentially to with a certain amplitudes and create this wave, right? So that's the Gaussian wave already has quite a few such modes, and we take the beams and we did some analysis, some mathematical analysis and realized that one can have one can associate with them a wave vector and direction, and essentially the distance over which you can confine light in that direction leads to a certain amount of diffraction and of the order of if this distance is d, then the wavelength of that light is lambda, so it causes a spreading of lambda by d. Right? And towards the very end, for example, in your lab, one can kind of estimate what sort of spreading one should get if I have light getting out from a semiconductor diode laser as an example. Right? And the lambda, if you look at red, it's 650 nanometers in air, and the distance of a waveguide in semiconductor is about 0.2 microns or 0.1 micron, and you can calculate from here what should be the spreading of a beam as the laser beam gets out of a semiconductor laser diode, for example. And that's how it's connected to what we spent time in the first part of the course. Gaussian beam optical resonators. So essentially, we take the light and now we put it between two mirrors, right, and let it propagate and let it bounce back and forth. And then these resonators give feedback. So essentially, if I have somehow created this light and it bounces back and forth with reflection coefficients of R1 and R2, we can find out how long will the light stay there, and before it leaks out. Every time there's a hit here, there's a certain fraction of photons that are escaping, and so the resonator was characterized by various quantities like cavity, like its finesse or its quality factor. A classic example of a quality factor is if you take glass and you have a tuning fork and you essentially try to create the acoustic vibrations inside. Quality factor is how many waves will it survive before, meaning how many cycles of waves will it ring for, right, before the sound escapes from the top, right? Exactly in the same way, how many times photons go back and forth before they escape from the cavity is the quality factor, right? So these two, so this is a feedback mechanism, right? And we made some analogies earlier on to electronic circuits, that if you have two things in your box, one is feedback, the other is gain, you can make an oscillator. So essentially, those are two things you need: feedback and gain. So feedback, we create. The first part of the course, we spent time understanding how light beams propagate, and then we said that we want to make an oscillator out of light. And therefore, I need feedback, and your feedback is a cavity. And then second thing I need is gain. And for that, we went into interaction of radiation with matter. And that's where we kind of talked a bit about quantum mechanics, not too much initially. And I'll just make a connection there. And we start out from so what we said, that how do we get gain? How do we get gain of photons? That concept is absolutely central to the laser, right? I mean, the gain of photons. And that came about because of stimulated emission. We talked about that in many times. We repeated that also just to emphasize that that's what makes everything possible about a laser, the stimulated emission part, right? And it's in the name. And so we started with blackbody radiation. And in an effort to understand blackbody radiation, Max Planck had to postulate that light energy is not continuous but comes in packets, and that's the idea of the photon, right? So whenever I write that the total, let's say, energy in carried by photon of oscillating frequency nu21 is h nu, that's the energy. That's already invoking quantum mechanics. That times the number of photons is equal to the total energy associated with that light beam. Now the major difference is now this number of photons is an integer. It cannot be half. It's 10 or 10 to the power 9 or something like that. It's an integral. So light beam at a certain frequency can only give you energy at discrete steps where this is an integer. So that was the quantum mechanics. And why do we know that this is necessary? Because without it, rather, this is what was necessary to explain experimentally observed blackbody radiation patterns, right? And that's how we realized that photons are carrying energy in these discrete packets. And this was done in 1905, and I'm just going to go through this again. And it took almost 12 to 13 years for Einstein to realize that this concept and blackbody radiation allows for the idea of stimulated emission. So about roughly about 100 years ago is when stimulated emission concept was introduced by Einstein. And so I'm going to skip a few details, just that the energy, once you quantize it, you can explain the whole blackbody radiation curve. Now, this was the contribution of Einstein, who said that I want to explain the blackbody radiation curve, but by looking at the actual optical processes that occur. And there are three processes. If I have electrons now in atoms that are have two levels, an electron is sitting at the higher level, it can spontaneously decay and emit a photon. Or if there are photons that are coming in and it's sitting at the lower level, it can absorb and promote itself to a higher energy, or get the matter gets excited, but the light loses some photons. So the intensity goes down. That's absorption. And if you kind of run this picture backwards, time reversal, then you get the opposite. Basically, less light comes in, and there are atoms sitting that are in an excited state. And if the energies if the energy of the photon kind of matches with this, and then it generates extra photons by downward transition, right? And the beauty of this process, which is the stimulated emission process, is that every photon that this photon stimulates, the atom to emit, will have the same frequency, as the same polarization, same direction, and same phase as the incoming photon. So it's completely coherent with that. And that is what makes the laser possible. This exact process, the stimulated emission, and this is where the gain comes in and adds to your resonator picture, because you have a certain number of photons in and you have more out now, right? And as we know also from electronics and microwave electronics and transistor amplifiers, the gain is for nothing. I mean, you're not creating gain out of nothing. It needs energy to hold the atoms in this state, right? And you are pumping energy into this system to hold it in state, and some part of that energy is getting converted into photons here. That's really what's happening, right? And the energy, so this state is, for obvious reasons, called the population inversion state, where population is inverted from its normal thermodynamic situation. Right? So that's our gain, and your feedback plus the gain, in pictorially is just one coming in and maybe two going out, right? Should get an oscillator, and that's really, this oscillator of light is what we are saying as a laser. So we went in and said, used actually Einstein's way of approaching this problem, that spontaneous emission, which the photons are emitted in every which way. They don't even need an existing photon to exist, trigger it. But all you need is some atom sitting in the higher state. So that's our spontaneous emission rate. Absorption rate has a B coefficient. It depends on the number of atoms sitting in the lower state, but it also is proportional to the amount of light that's incident, right? So both absorption and stimulated emission need a photon to get it going. And all our laser equations, gain spectrum, gain saturation, QSwitching, mode locking, all come from here, right? If you remember the Einstein AB coefficients, all the rate equations for semiconductors, for normal Heine lasers, solid state lasers, they all come from here. They're basically, in the end, just a few more steps from here and you'll get it, right? So just to make that connection at this point. So I will essentially kind of, okay, so what you do is look at steady state and then by equating the Einstein A-B coefficients, you realize that A and B coefficients, because this picture should explain the Planck blackbody radiation, the A and B coefficients are actually intertwined, and A over B is related to speed of light and Planck's constant and the frequency of light. Just to be clear, A and B are not constants. They depend on which photon energy you're looking at, right? And that information is in the wavelength here, or the frequency here. And okay, so by this connection, you realize that they're connected. I mean, the Planck's formula and the light matter interaction is connected through this relationship. And then just to be clear, Planck did not have this idea of A and B coefficients at all. I mean, it took almost a decade after that to get this out. Yeah. Okay, so now getting more specific about the laser, whenever you do a measurement, you see that there is a certain width to the emission spectrum, be it of a hydrogen atom. If you excite electron and look at the spectrum of hydrogen atom, you see there's a certain width to the transition in frequency or energy. It's not extremely sharp, but there's a certain width. And then we realize that this may be because of various reasons. All those reasons lead to the fact that if I'm getting a photon that is not just at mu21 or nu21, but they all must be because these are broadened, right, by some means, some physical means. Either the atom is moving, colliding, doing something like that. There's some broadening associated with it. So we model it and say that there's a certain line shape to the way this optical transition can occur. Right. And that line shape should be such that its total integral is 1. And now, depending upon the nature or the physics of that broadening process, it could be homogeneous, meaning all the atoms that are giving you the gain are acting the same way, they're getting hit or broadened the same way. That's homogeneous. Or it may be inhomogeneous, in which case there are different emitters that are getting effect in different way, moving with different velocities and getting Doppler shifted and all that sort of thing. Typically, a homogeneous broadening will lead to this Lorentzian sort of line shape. And kind of in the last class, when we do this quick survey, you can explain the Lorentzian broadening from both classical mechanics of an oscillator, harmonic oscillator picture, or from completely quantum picture too. Okay, so I'll kind of step through this a little bit now and say that when we look at the radiative transition rate now, we have a spontaneous emission part and we have a stimulated emission part, right? And for a laser, this dominates above threshold, right? And this dominates much below threshold when you have LED behavior, light emitting diode behavior. Spontaneous emission dominates. But once you reach the threshold current or threshold injection intensity, then this starts dominating, much larger than the spontaneous part. Did an experiment also for the semiconductor diode where you see the ratio and there's a certain change, sharp change at the threshold. The rate is proportional to the cross section, stimulated emission cross section, and the cross section depends on the material itself. Cross section is in per centimeter square of the order of 10 to the minus 12 to 10 to the minus 20 centimeter square, right? Of the order of, and you've seen that, and I think you're also designing your current lab 2 assignment where you need these values. Depends on the Einstein A coefficient, wavelength square of light times the line shape, and there's a refractive index sitting in the denominator here. When you go to okay, so that's your cross section. The rate is cross section times the intensity over the photon energy. This is you need light to get your stimulated emission going, so you need some intensity to be present to start. And most importantly, the stimulated emission is obviously proportional to the population inversion. Right? Without it, you don't have stimulated emission. You actually have loss. Okay, so that's just to be clear. Cross section increases as the square of the wavelength, and the larger is the line shape factor for you. If you might GNU, the larger is the peak height here. The larger is the cross section. And this is the gain of the larger is the gain, the lower is the threshold you need to get it to lace. So that's the other idea. We went through this picture that if I have photons coming in and look at this, both for the semiconductor we did it again, but then this was done earlier on, that if I have a certain number of photons coming in and apply this rate equation model and say that how many photons are coming out. What I want to know is what is the intensity of photons. Intensity, which is the intensity at a frequency nu, is always proportional to the electric field square. But in the earlier part of the course, we never really quite talked about the electric field, for good reason. Essentially, we said intensity, I'm going to look at it not as proportional to electric field square, but as proportional to the number of photons, pretty much. That's how you look at the intensity. So you kind of push the details of the electromagnetic structure of the laser beam. When we were doing that part under the rug, we don't get into that too much at this stage, right? But we said that intensity here, if I have stimulated emission, I'm adding more photons, so I'll just add the number of photons that is stimulated and get an increased intensity as if I go through a gain medium. And then if you just do the bookkeeping for that and say what is the net change in intensity as you move through a gain medium, you get your this is the rate of change of intensity, and you have all the gain spectrum sitting in front. So what you get is really that the rate of change of intensity as the light beam goes through space in the direction z is equal to against whatever is sitting out here in the front of this. It starts out as a linear term. Whatever is sitting out here as a function of frequency is what we call as the gain coefficient now, and that's what you call as the low or this is the low intensity or small signal picture. If I have very high intensity, then we know that laser also, you will saturate the gain because you don't have an infinite number of atoms that are giving you gain. Every time I'm getting a stimulated emission, I'm losing my active species, right? So I'm losing the number of atoms that can give me gain because every time. So gain saturates, so there's saturation intensity. So really it's a nonlinear equation. If we neglect the denominator, that's what's called small signal, meaning the intensity of photons is low enough that you're not saturating it, right? And then whereas the saturation intensity gives you the dynamic range over which you can get gain. If you reach that, your gain will saturate. It's not going to increase anymore. Right? So that's your equation really, which has varies inside it a lot of microscopic details, but the basic notion that one should take away from here is for small signal, the intensity at any distance z, if I'm going through a gain medium, right, it is increasing from the value 0 to as e to the power gamma, which is the gain coefficient times z. So you're exponentially increasing the number of photons, and that's really what's happening, right, as you go through a gain medium. And obviously you need the physics of the microscopic details of this gain are captured in this whole factor that it's proportional to all this 8 pi n squared, the line shape. That's one factor, right, which is your cross section, units of cross section here. A21 times the gain. The line shape, that's dimensionless, and lambda square is length square, so you get centimeter square units here. And then the second factor has to do with the population inversion minus, as you see, the degeneracy factor G1 and 1. And in a standard atomic system, gain system, the n is in 1 over centimeter cube, which is how many atoms per unit volume, right? Right? And cross section is in centimeters, and so your gain coefficient is in inverse centimeters, 1 over centimeter, and that's how it should be because this is in length and this should be inverse length, right? To be consistent here. And typical gain spectra, again, if you look at let's say 10 to the power minus 18 centimeter square, and atomic density in if you look at a gas laser, it's typically somewhat of the order of 10 to the power 18 per centimeter cube. So your gain order of magnitude would be roughly like 1 inverse centimeter, roughly, right, for that situation. And If you have packed a lot more, we saw later on in the course that in semiconductors, you can actually get way higher gain. Gain spectrum would be, it could be 1,000 inverse centimeter, right? And such things in a typical semiconductor, right? So, okay, so that's your gain, the idea of gain, and then what we now go back and just to connect back to the picture, what we are saying is now I'm going to make an oscillator here, and I want to know how much power is it going to radiate. Right? How much power can I generate in the oscillator? It's the same game. If I'm making an oscillator in an RF microwave system, I want to know how much power can it generate and how high or what frequency can it generate at. Same game with the laser. If I am at blue wavelength, if I am infrared 1.55 micron wavelength, how much power can I, make this laser radiate? And I think we know that the power it has uses across the board. If you have very low power, you tune it down and you get into single photon regime, and then you can do some interesting things with it. You tune it up, go to very high photon intensity. Essentially, larger the number of photons, the more information you're going to push through. Essentially that's the more classical information you can push through, because there's always loss, and you need to fight that loss with large numbers. That's the idea of gain. So broadening, there were a couple of mechanisms. There is homogeneous broadening, which leads to a Lorentzian sort of line shape. So just to be clear, what I wrote here, this picture, is only true for homogeneous broadening here, meaning the denominator is 1 plus intensity over saturation intensity for homogeneous broadening. If you have inhomogeneous broadening, specifically a Gaussian broadening, then you get a square root here. So I'm just trying to point that out at this point. And both will lead to gain saturation, but in a slightly different functional form. So it's, the differential equation will be slightly different. To add in a little bit more detail, you always also have a little loss. So you always also have a little loss coefficient here times I nu. So that's your full-blown equation now, really, how intensity changes through a medium. So, okay. Now, one of the most classic ways of homogeneous broadening is atoms are colliding with each other, right? So as the atom starts getting ready to emit, it started emitting a few cycles of the laser light. If it collides with an atom and suddenly goes in another direction, then its phase is kind of randomized, and this is kind of your cycles. The laser is coherent for a certain amount of time, and then it changes and then changes. So in time domain, you have a delta t introduced as to how certain is it, with how much certainty in time do I know it started emitting at some point, or what's the phase. And that delta t in the frequency domain is what leads to the broadening, and that's the classic case of a it's called collision broadening because of atomic collisions with each other in a gas laser. This doesn't quite show up very much in a semiconductor laser because there the atoms are sitting in a crystal, but then there is also collision because there's electrons going through and they set off these phonon vibrations, and there's also that sense, a little bit of that sense in a semiconductor laser too. Okay, so I'll actually, and there's inhomogeneous broadening, and classic case of that was discussed by Cliff in some detail was the Doppler broadening, where you have a lot of atoms, but a lot of them are moving in one direction, the other, and half of them are moving one direction, the other half in the other, and so the laser beam kind of sees the frequencies add in one direction and subtract in the other. So as a result, when you do the math, you get that this broadening is actually Gaussian. The line shape is Gaussian for the situation. So and what's sitting inside that broadening parameter is how fast are those atoms moving. And that's why there's a temperature term in there too. Temperature tells it how fast kinetically should these atoms be moving in a gas, and that's what determines the broadening. So if you cool it down, then you will lower this inhomogeneous Doppler broadening. But okay, so and this is experiment true. You can take that and you can cool it down, and you see the broadening go down. Okay, I'll actually, and then we came kind of to a summary of the laser again. So you have the gain medium now, put it all together. You have a resonator around it for feedback. And then the gain spectrum as a function of frequency looks something like that. And the loss spectrum, which combines losses at the two mirrors plus any intrinsic losses inside here, looks something like that. Typically, it's never like that. Typically, the frequency spectrum of loss is, if I look at a frequency spectrum of loss, it will, kind of maybe look something like that. Except the laser line width, the gain spectrum is, in a frequency domain, if you start from 0, the laser line width is actually extremely sharp. So within that window, this thing looks like a pretty flat. Right? So that's the physical meaning. Why is it shown like a straight line, a constant value here? And then whenever the gain you are getting by population inversion, generally there's loss. So generally there's loss, and then you inject more and more energy into the system, and finally your gain goes above the loss, right? And then that's when you get the threshold for lasing, and then that can be calculated basically from a round trip path, right? You go say, I'm going to start out the light here, go through one gain, e to the power gamma Lg, sort of increase in the photon number, go here, lose some, maybe lose some here again, another gain. So you get this equation, and from here you can write down right away that how much gain do I need to overcome all the losses. If I have only mirror losses, it's very simple. It's 1 over twice the gain length times natural log of 1 over the mirror reflectivities, right? It's a very simple result, and this is something you should really take away from this course. If you want to talk lasers to any, people who use it, physicists or engineers who use it for communications, this is kind of the central equation that you should kind of have in mind. That just to be very clear, the gain threshold has nothing to do with the gain media at all. Just to be very clear, the gain threshold that you need to start lasing has everything to do with the loss, nothing to do with the gain medium at all. Right? What we are saying here is I can give you any gain you need, but how much gain do you need to just get me lasing, right? I mean, that's the idea, the question we're asking. So the gain spectrum has only, it has one thing, which is the length of the gain medium here. But the physical loss is what captures it. It doesn't care at all what atoms you put in and all that sort of thing. Does that make sense? This is just to be clear. We say it's the gain threshold, but it actually has got to do with the loss here. And then, okay, so once you have that, you can have, the cavity here, or the resonator determines all the modes that are allowed. And if a few modes fall within the gain spectrum, then it will be a multi-mode lasing, or may not lase. I mean, you may say amplified spontaneous emission at various wavelengths. I think you saw one of those examples in your lab 1, where you had many modes that were not yet lasing, and then once you started lasing, it locked into 1, and that becomes a single mode laser. Sometimes this doesn't is not happy to do it. If you have inhomogeneous broadening, it will try to lase in multiple modes. And then what you do is you put in another thing here, which would be an echelon, which kind of says that you change your FSR. Then, right? I mean, that's so, and then have only one. You push out all the other modes and leave only one inside here, right? Inside this gain spectrum. So that's could be a Fabry-Perot echelon or a external cavity, mirror and things like that. Okay. Okay, so now looking a little bit, so we did some work on gain saturation. What is the saturation intensity? Typically, just off the bat, you can write down the saturation intensity or estimate the saturation intensity of a laser by saying photon energy divided by the cross section, which you kind of know from the material, divided by a lifetime. And this lifetime is related to the downward transition, and from the rate equation, it comes out. You kind of know the lifetime from a rate equation or a measurement, and then that kind of gives you the saturation intensity. And then based on that, if your light gets in and you start amplifying it, the intensity starts increasing. Then if your length is a certain distance, you will get exponential increase. If your length is much longer than what you will saturate it at some point. You won't have any further increase, right? So you kind of go over from an exponential increase in intensity to kind of it saturates. It doesn't quite saturate. It's kind of a very weak or linear increase after that. So that's what happens here. More importantly, you can look at the dynamics. As you start off the laser, if N1 and N2 are changing in a certain way with time, then there may be a certain window within which you get N2 larger than N1, not for all steady state. That will only give you it won't give you a continuous wave laser. Basically, I'm saying that as I start off, depending on the rate equation, if my N2 is increasing like that, it will saturate finally, and N1 is increasing like that. Let's say, as an example, it's not a good idea for a laser, but with time, when I start, so I have only a small window over which I get N2 minus N1 is positive. So it will actually laze within this window, but then it will turn off, right? So you don't want this situation. Typically, if you want a continuous wave or CW laser, there you are looking for the opposite, where it's okay to start out the N1 higher, but N2 should dominate in the long run in some sense, right? So does that make sense? So then you get a continuous wave laser. If N2 is always above, that's okay too. I mean, that's not a problem. In fact, it won't be always above because you start with equilibrium when N1 is larger than N2. But anyway, so that's what we're looking at this point. But more interesting dynamics of the laser are you make use of the fact that you can find out how the N1 and N2s evolve with time, and you can then I'm going to skip a few things here. You can then go and do things that are impossible to do in the CW, that you do in the time domain now. Meaning, here this difference is basically steady state, and it's clamped, and that's going to give you a fixed gain, because gain is proportional to N2 minus N1, and therefore, in the end of all that, you'll get a fixed output power, right? And this output power typically is not very high, really. It's maybe hundreds of milliwatts or something like that, right? Depending upon the gain medium and all that. But then making use of the fact that there's a lot more you can do in time domain, you can generate pulses of extremely large power now, into megawatts or gigawatts now, but ultra short pulses, very short pulses of light, by playing games in the time domain. And the two games that we discussed in this course were the QSwitching and the mode locking. Okay, so these were the two methods of getting much more power, but for much more intense power out of lasers, but for very short amounts of time, or in other words, very ultra short pulses. And the idea there was, just so you have, this is your DC continuous wave output power, but typical mode lock laser, you'd be looking something like this, very sharp pulses of much higher power. And this, how much higher it could be, really in the domain of 10 to the power 6 watts per, or 10 to the power 9 watts, gigawatts or something like that. It can get up there, so meaning the maximum power. Okay, so I think we did discuss why a two-state system will not give you a laser, continuous wave laser, but three-state will, and four-state is more preferable, and went through some details here. Looking at Q-switching, what's the idea of Q-switching? If I have both the mirrors on, then the gain always gets locked. Once it hits loss, it cannot go too much beyond. But if you remove one of the mirrors, or you have a shutter that takes it off resonance, then basically you can pump it very hard, and you can have extremely high gain than the threshold gain for lasing, and then you have maybe 4 or 5 times the higher than the gain that's allowed in steady state. And then you close the shutter and you make it meet the cavity condition or resonance condition. So now essentially what it does is it will try to dump a lot of power in a very short time, and you get in a Q switch laser. Hopefully you can see you're switching the quality factor of the cavity. That's what you're doing. That's what's a Q switching, right? Switching from a very low Q, where the light could escape easily. All you're doing is building up the gain medium, to a very high Q suddenly, where then the light has to it has to fit into one of the modes. So essentially you get a very high power, but then it kind of decays, and you get typically nanosecond or slower pulses here. And the mode locking, on the other hand, I think I'll just the idea was you have again the gain medium, but you have a modulator which has an optical window that is either opens or closes at a certain frequency, or modulates it. And then by doing this round trip path, this was probably the most intense math in this course. By closing this path, you can say what is the mode lock frequency, how much energy do I get here, what is the line width of this, and all that sort of thing. You can calculate from here. So one of the ways to do the mode locking is instead of having an active modulator, you can just put a saturable absorber, and we talked a little bit about that, which has a time domain response that the optical pulse itself unlocks changes the saturable absorber from an opaque medium, and you increase the intensity as the pulse comes in, and at a certain point it makes it completely transparent. So that's the saturable absorber, and that picture should also make sense because the more photons you are pumping into a material, you are kind of going towards more gain, and at some point you become transparent, right? So that's the transparency threshold of any material, when photons get in and when the gain and loss become equal. So I'll skip through a few of these. We discussed quite a few different kinds of lasers, dye lasers, TISAFs, and as examples, neodymium YAG, CO2 laser. Here the gain was not because of atomic transitions as much as vibrational frequencies and things like that, right? We had manifolds of energies, which is why the CO2 laser actually turns out to be extremely efficient and very high energy. It's not miniature, but if you look at very high energy requirement, this is what's typically used. We looked at excimer lasers. And we had a very brief discussion on free electron lasers. This has a physics that's very different from all the other lasers that we talked about. Right? Finally, semiconductor lasers is basically a culmination of many of the concepts we talked about earlier. It essentially uses all these ideas, right? All these ideas, but it's an application in a material system now, or in other words, the laser with a semiconductor. The size of the laser is the key enabler of many interesting applications. Essentially, it's less than a millimeter size pretty much, and its outputs about the same amount of power as a tabletop meter-long laser. So that's why it can be integrated on chips, and it's extremely efficient. Not only that, you are driving current. Your excitation method is not another laser, but it's a current, electrical current that you can apply with a battery now, right? A small battery. And as a result, you can have on-chip, not only that, you can take this battery and you can modulate that signal at very, very high frequencies that you cannot do with a very large tabletop sort of structure. So as a result, this is the heart of much of the optical communications today, as I was kind of started out today. So you take this laser, you have laser beam that comes out, and then you start modulating this and see how fast is it changing, and that's how you transfer data, right, into optical fiber, for example. Details of the semiconductor laser: it has exactly the same physics as most others, except the joint density of states is what makes an appearance here. The joint density of states is, instead of a two-level system, a semiconductor has a band of states. When you put the electron in the crystal, it can assume, and you subject it to the quantum mechanics with a periodic potential, you get a density of states that looks like that for electrons, and these are unoccupied states, these are occupied states. But then to create population inversion here, you need to inject holes or pull out electrons from the valence band and put electrons in the conduction band. So that defines these two quasi-Fermi levels, Fn and Fp, or Fv. And if your quasi-Fermi level for electrons enters the conduction band and the quasi-Fermi level for holes enters the valence band, then you got population inversion, and that's the criterion for lasing in a semiconductor, or gain in a semiconductor. So the joint density of states appears here instead of the line shape. In a semiconductor, joint density of states appears here, and instead of the standard population inversion, which is for a two-level sort of system or such, here you have bands, so your Fermi functions appear here. Conduction band, Fermi, and function, occupation probability minus the valence band, Fermi function. That's the correlation between the two. And after some math, we figured out what are the joint density of states. We saw that if you go to nanostructures, from 3D to 2D to 1D or 0D, you can shape the joint density of states. As a result, you can shape your gain spectrum. Right? You can design and the other thing is the magnitude of the joint density of states in semiconductors is when you look at this number, you get a very high number, is what I mean to say. Kind of, that's what leads to this, 1,000 or inverse centimeter sort of gain spectrum. Okay? And then I'll say that as we, if we start out at equilibrium, you only have loss, but as you inject more and more carriers and you overcome the gain threshold, I think, so I didn't write that here, but you essentially the sign, this sign changes from negative to positive, and you get gain instead of loss now. Okay? And from that you can calculate your spontaneous emission spectra, your stimulated emission spectra, and such things. And you did that anyway. I'm going to now the optical waveguiding in a semiconductor and the design of the mirrors is all done typically by engineering the dielectric constants. So you don't typically put in another mirror, but you change the dielectric constants. So if you have your active region which has a larger dielectric constant or a larger refractive index, then light gets guided automatically in that region. And then you go to the edge of the sample and you have mirrors because of refractive index mismatch between the material and the air. So you get these two mirrors, and then that's how these structures are made. And basically by changing the active region, you could lower the thresholds currents for lasing over 4 orders of magnitude over the last 3 or 4 decades. So that's now they're extremely low current threshold lasers with quantum dots and such things. Okay, so I'll essentially go over towards the very end, and those were the so for this I would say for the exam, just make sure that you kind of get an if I ask what is the threshold, can you calculate the threshold given the semiconductor has this much gain, and or it has this sort of quantum wells and all that. So you had a couple of examples like that you did in your last assignment. So just we'll have a couple of those in or maybe we'll definitely something like that will appear in the exam, I would say. Okay, so the last thing, just maybe a minute more, we could develop for a very simple phenomenological model of a laser. Instead of going into all the details, you can say that, well, I'm going to measure a laser and you see that it looks something like this, right? And then say that can I go back and bury in some sense all the physical details into some parameters? And indeed you can, and this phenomenological model tells you that till a certain injection current you get spontaneous emission, and then above it you get stimulated emission. And when you get stimulated emission, you really increase the efficiency of conversion of energy from electrical injection current energy to photon energy in a very drastic way. You really kind of increase the conversion efficiency when you get there, and that is captured by this slope here. The sharper the slope is called the differential quantum efficiency. And then you can say that if I sit here now and I start modulating my current, how fast is the photon intensity going to follow it? And that's what led to this cutoff frequency of a laser. And then that's related just to the cavity parameters and some lifetimes inside the cavity. Okay, and here are some examples. These are on the slides of real experimental data on semiconductor lasers used today, and that go with all the other things we talked about. Okay, so what I'll do is we did discuss some survey things later on. We discussed how from classical electromagnetism with some very simple equations you can estimate the A coefficient, because A and B coefficients we never said how you get them, right? That was where we ended the course by saying that I can give you A coefficient from classical electromagnetism by comparing it to an antenna radiator. And if you want to go a little bit more and you want to go and say I want to do it by quantum mechanics, what you do it is the two-level system interacting with the oscillating electric field, which is light. And when you do that, you get these, Rabi frequency and other things. But essentially, a two-level system, can explain to you, also give you the B coefficient for absorption. But from there, you can recover your A coefficient. And it turns out it's very close to the classical value that you evaluate. And I want to end here by saying that this picture of a two-level system, which is driven by light wave or some wave, and it's oscillating, this is what is today called as a qubit or a quantum bit. It's exactly this thing. There's essentially you have a two-level system, and light comes in, and it starts interacting, and then if these light matter, so half of the time, if in some sense the energy is in light, the other half it's in matter, right? So it's going back and forth. It's a LC oscillator sort of thing. And if you don't have any loss in the system, it preserves the quantum information for a very long time. And then if you can use this sort of a picture, this sort of hybrid light matter, this is a qubit, and it can help to do communication in a secure way. It can help to do computation instead of bits where zeros and ones. You can do it using much larger phase space, if you might. I mean, so it can potentially enable quantum computation. So it's kind of a good point to end the course, because I think this is the ideas are here, but people don't yet know how to make them work. And so it's just about starting now. And I personally believe light will play a very big role in this whole game, if at all it succeeds. And it's kind of nice, because light is what led to, as you know, explanation or discovery or development of electromagnetic theory. Right? Trying to understand light led to the invention of the development of quantum theory, right, by Planck. And then understanding light also led to the development of relativity and gravitation by Einstein, right? So the biggest revolutions in physics have been just trying to understand light, right? And now we have in the laser a mechanism to create light in its purest, kind of indivisible form, right? And so I think there's a huge opportunity, in some sense, to make discoveries that are really fundamental, and probably will, in terms of, what we say is the amount of data we communicate today kind of makes, people had thoughts of how much data could we communicate, right? And in 100 years, we are doing 10 to the power 7 or 10 to the power 8 more than what people thought was possible. And I think these things continue happening, meaning if we figure out some other angles to light and how it interacts with matter, there will be orders of magnitude improvements, which most people cannot believe today, but has always happened in the past, because you make a new discovery, and then it opens up many, many new windows. Okay, good. So, all right, I think we are over time today, but I also want to kind of thank you for sticking through the course. I think it's definitely was an experiment with Cliff and me, kind of going back and forth. Hopefully you enjoyed it. Hopefully you are enjoying the labs now, and I really hope you share the excitement of the course. That's what we, as instructors, can always do in a course. All right, thank you very much.